Thank you. Thank you very much for the invitation to speak here. So I will speak to you about some joint work I've been doing with Louis-Pierre again and Bourgade for both probabilists, and the work is still quite, it's very much in progress. So I will report some preliminary results. So the function, this twisted divisor function I'm alluding to in my title is the following one. So you take an integer n and the real number c, and you take the sum over the divisors of n, sum and d to the ix. Okay, so it's a pretty classical function. Maybe you've already seen it in some context.
It's usually got a different notation. I'm surprised. Sigma ix of n is the standard notation. Sigma k of n is the sum of d divides n of d to the k.
Right. Some people might use this notation, I agree. Okay, so this is a multiplicative function. So it appears, you can study various things about using elementary tools. And the reason why I'm interested in this function is because it is the Fourier transform of the sequence log d, or d divides n, of the sequence of divisors of n. So if you want to understand various properties about the distribution of divisors of n, you might as well, it's a natural thing to try and consider this function and to understand this function instead. Okay, so maybe I'm going to tell you some of my favorite things about divisors before I jump into this object that maybe you have heard before and are more familiar with. Okay, so here are some results and classical questions about divisors. So the first one, the results, maybe this is the results on the physical space. So the first one would be one of the most basic things one can ask is how often an integer has a divisor in some interval. It's fixed. And this is related to an old question of Erdős about the multiplication table, how many elements it has. So Ford studied this question and he showed there is about x over log y to some constant delta log y to the 3/2, where delta is 1 minus 1 plus log of 2 over log of 2. Okay, it is what it is. It's actually the probability that a Poisson random variable of parameter 1 is bigger than 1 over log 2. Well, it appears in the exponent of that calculation. So it's not so unnatural. It appears naturally, but it's funny looking. Okay, so an open problem, for example, here. So this is a theorem before.
Is this uniform in all x and y, or is there some restriction?
Okay, no. So it would be uniform, let's say, up to root x. And then you can flip y and x. You can switch y to x over y. So that was proven by Ford in 2004. And okay, so this is what we know, but an open question is whether there exists an asymptotic formula. So whether I can replace this with a tilde constant times this function. Is there an asymptotic formula? Is there a more precise asymptotic formula? Don't know. Yeah, so even if there is I guess the easiest regime to study this question would be when y is x to the little of 1. Would be the easiest regime because what about small prime divisors of n? Okay, so a second problem about divisors is about the Hooley delta function or the Erdős Hooley delta function. Delta of n. So this counts how much concentrated. So it's sort of in the other extreme. This is just asking about one divisor. The Holy delta function asking how much the sequence gets concentrated. So you take the maximum of all counts, let's say in a dyadic interval, or you can choose any other. Usually you choose any adic interval, but this doesn't really matter. Overall hue. So this is the Erdős-Khoury delta function. And you can ask various statistics about it, and we don't really know the answer to them. For example, you can ask how big is delta n for a typical value of n. We don't really know. What we know is it's between two constants of 2 powers of log log. So what we know is that delta of n is bounded by log log n to some weird constant 0.61 something, I think. 0.3. And from below by log log n, and then 0.3533, etc. So this is due to Kevin Ford, Ben Green, and myself. And this is due to the Dimitris and Tenenbaum. And both of the results improved on earlier work of Meyer and Tenenbaum, both on the upper and lower bounds. So they're quite recent. So this is from, well, the preprint is from maybe 3 years ago, but it should be published this year.
It's an individual, it's not almost.
That's almost surely, sorry. Asymptotically almost surely. So you exclude the zero proportion of n. And the Dimitris and Tenenbaum put their preprint last fall in the archive. And okay, another thing you can ask is, okay, what about averages of delta n? So what would this be? And here the results are even less satisfactory. So we know as a lower bound that it's at least x log log x, and as an upper bound, the best thing is something like x e to the c root log log x. And this appears in the book of Hall and Tenenbaum. I'm not sure what's the right reference for this. And this is the same paper of Hall and Dimitris and Tenenbaum does this. Okay, so if you care about divisors, these two questions have they have been studied a lot, and they're two of the most important ones. The delta function in particular is quite fascinating because it has, when it was introduced by Khoury, it was introduced in connection with some questions in arithmetic geometry and counting solutions to certain Diophantine equations. So it has surprising applications in other contexts.
In your question on the left-hand board,
yeah,
are you saying that it's plausible that there isn't a precise asymptotic formula, or are you just saying find one?
I would conjecture there is one.
Okay, but that's not sort of.
But well, we don't know at all. Okay, so these are two classical questions on the physical side, and what about let's see, a question on the spectral side. So what is this question that I will be studying? So it's about how big, it's about the supremum norm of this 2C divisor function. So you take tau of ndiξ, and then you take the maximum of it over some interval. And just to be clearer and avoid too much notation, I'll just fix the interval 1, 2. And let me call this capital Tn. Okay, so what is the distribution of the supremum norm of this function in this interval? So what is the distribution of it? And in particular, Hall and Tenenbaum, in their book Divisors, they have a question where they ask, what can you say determine optimal C such that our C is less than or even closer to less than log n to the C plus little of 1. Asymptotically almost sure. So again, for a typical integer n. Right. So this is what they asked. The reason why I'm staying away, I'm fixing this interval, is because I don't want to go too close to 0, because of course then the question becomes trivial, or not trivial, but well understood. So if you were to ask when x is 0, what happens when x is 0? Well, of course, then your function is just the divisor function. Of course, this is the biggest it can be. Right, I also write my divisor function by tau, which also, I'm assuming is also not standard.
No, that's okay.
Right. And this, we understand this distribution very well. It's basically 2 to the number of prime factors. Very roughly. Well, it's actually
the place where sigma is used is those kind of sums of Fourier coefficients of isomorphs.
yes.
That's what that does.
Yeah. Right. So it's basically equal to this, and we understand, let's say, from Hardy-Ramanujan, from their work in the 1930s, we know that omega n is close to log n almost all the time. So then tau of n is log n to the log 2, something like that. Maybe some have to leave a little of 1 here. Okay, so that's why I'm going to stay away from 0, because it completely changes. Of course, you could ask, okay, what if I let C close enough to 0 as a parameter of how big my integer is? Okay, but now this problem is already complicated enough on its own, so I'll just focus on that. Okay, so there is a way to abstract a little bit the problem. Because this problem is not really about integers. It's much more a probabilistic problem than it is about integers. So let's say that n is square free. Then we can factor this function as a product of all prime divisors of n. And then it's a product of 1 plus p to the IXC. And I can think of this as the following. So let's say my integer n is up to x. Then I can think of this as or model by the product over all primes up to x of 1 plus bp times p to the IXC. And what is this bp? bp is a Bernoulli random variable. Of parameter after 1 over p, and they're mutually independent. Each other for different primes p. Okay, so right, so the proportion of integers divisible by p is about 1 over p, and if you take different p and q, well, the proportion is 1 over pq, which is the product of 1 over p times 1 over q. So there is some sort of rough independence. So I can just forget about integers and just think about this model if I want. And there is a way to make this precise. So if you don't like integers, you can just think about probabilities. And what is interesting about this product is that it reminds us of a similar relating product that appears in the theory of the zeta function. So let's see. A similar product appears in the theory of zeta. Okay. So what is this connection here? Okay, so let's look at zeta 1/2 on the critical line. Let's say at height t. So of course we know that the Euler product for zeta doesn't extend to the critical line, but in certain questions, like for example, questions about statistics of values of zeta, at least on, if you don't ask refined enough questions, then you could think of zeta as basically a product going up to t. So this is accurate, okay, for certain statistical questions. With t here being just being a uniformly chosen thing between 0 and t, capital T. So if you think of t as being uniformly sampled between 0 and capital T, little t, between 0 and capital T, then you might think of zeta as being basically this product. Then when you sample t uniformly at random from this interval, then this p to the it's sort of spin and they could distribute across, on the unit circle. They could distribute independently or quasi-independently on the unit circle S1. So I can think of this of zeta, so then I can model zeta by the Euler product p up to t 1 minus xp over p to the 1/2. Okay. Where this xp are uniformly distributed on S1 and independent, mutually independent. Okay, so if you think of zeta in this way, you motivate very naturally various famous results about zeta, and most importantly, Selberg's central limit theorem. Okay, because now if I take logarithms here, then this becomes, if now I take the log of this product, maybe I'm gonna, the log of zeta is basically this sum here, xp over to the 1/2 plus all the terms. And what do I know about these coefficients here? These are no variables. Well, I know that they have mean 0. And they have variance 1 over p. So then this leads me naturally to Selberg's let me call this script P, which is telling me that this script P random variable is, or rather log of this, is roughly normal. Oops. I want to take, sorry, I want to take absolute value of zeta. So I should be taking real parts here. So if I do this with real parts, then I get 1/2p. If you do it with xp, then you get the complex velocity. Okay, and if I do the similar computation for this random model, then right, then I'm gonna get let's see. So I have that if I look at these factors, then the expectation of this is 1/p to the 1 minus ixc. And if my xc is in this regime between 1 and 2, because this ixc spins around, this is small on average. When c is 1/2 in between 1 and 2, let's say. And I have the variance here. Vp c is basically 1/p. So here I'm thinking about complex variance because it's a bit easier. You can see the analysis. Okay, so it has some mean value that is actually when in this regime it's actually 0 again, and the variance again 1/p. So this computation I made here sort of leads naturally. For example, when if I take xc to be 0, then this would not be small on average. When xc is 0, it leads me to the Erdos-Katz theorem that omega n is distributed roughly like a normal of mean log x, variance log x. This is the Erdos-Katz theorem. And when xc is between 1 and 2, the behavior changes. And then you have this log tau and xc to be roughly a normal of mean 0. And the variance becomes p²/12 times log x. So it's just a commutation. Okay, so there is this analogy. And why am I mentioning this analogy? Because the question about maxima of zeta is very well studied.
Is there anything special about 1 and 2, or can it be taken to be any fixed constant?
1 and 2?
Or you said that c is 1 and 2.
Oh, I could just take any non-zero. 3 and 4, doesn't matter.
Could, I guess you'll probably discuss this at the end. You could replace d to the xc by a character, chi.
Right.
And I'm sure then, have you thought about that?
No. I haven't thought of it.
Okay, don't worry about it.
Okay. Okay, so right. So what about the maxima of zeta? So then what would be the analogous thing to do?
So your co-author lectured on this here 10 days ago in the probability seminar, and there were very few of these people here. So you.
Okay, good. Louis-Pierre or Paul?
Paul.
Sorry?
Okay.
Bourgade. Okay, so right, so I'm gonna so I want to understand what is the analogous question for tau for this one, T of n, the maximum for zeta.
He lectured on zeta and the, of course, branching process, and that the maximum as this 3/4 or whatever.
Yeah, I will mention all of this. Yeah. So here, what do? I sample n and I get my BP, and then I twist this by p to the IC. So what would be the analogous thing here? It would be to take xp and to take this factor and then twist xp by p to the IC, or by p to the minus IC. And if you actually do this and you think where xp is coming from, xp is just modeling p to the IT, then it would be the maximum over, let's say h for shift h of zeta 1/2 plus IT. This is my random position, and then my shift and my twisting. So this is the analogous question, because there is this certain rotation invariant of this p to the ITs because they're uniform on the circle. So what happens now is that this can be modeled by the product of p up to t. So it would be the distribution of this when t is uniformly distributed on 0t. And I model this by, the absolute value of 1 minus xp e to the 1/2 plus ixc. Sorry, h here. Okay, so I hope you can see the resemblance. I just have this BP, and I have this, which has variance 1 over p, and I have xp over square root of p has variance 1 over p, and here I have a shift, a twist by p to the IH, here I have by p to the IC. And again, the interval 0, 1 is not important here. I would have taken 1, 2, or 3, 4, 3, 2, 3, 4, etc. So there is this conjecture about this maximum of zeta that has inspired a lot of work in the subject. Okay. And it's a conjecture by by Fyodorov, Thierry, and Keating in 2012, if I'm not mistaken. They conjecture that this maximum is almost surely given by something. So actually, they have a much more precise conjecture. So they say, if I look at the measure of t between 0 and let's say, such that this maximum is 1 has zeta 1/2 plus IT plus IH, and I ask how often this is bigger than. Okay, this is some normalization thing. So the way they normalize is by looking at e to the y times log t over log t to the 3/4. Then for fixed y, this should tend to some limit, let's call it fy, as t tends to infinity, which should be asymptotic to c y to the -2y or something like that. Yeah. Very precise conjecture. So this first you take t to infinity, and then if you let y to infinity, then it should have this asymptotic behavior. Okay. So the goal then is to formulate some analog, to understand what is the right conjecture for T of n and try and prove some things about it. And actually, in some sense, it's an advantageous situation for T of n because we don't have to deal with the zeros of the Riemann zeta function and the Riemann hypothesis, which is one of the main stumbling blocks in obtaining results towards this conjecture.
I mean, you haven't mentioned Maury Bramson. Is that going to come? I mean, that 3/4 is.
Yes.
So that is sort of the highlight. You will explain it, right, in your case.
Yeah, so I'm going to explain now how one would even try and guess what kind of shape of a result one should expect and why we get this exact shape, actually. This is sort of the right order of magnitude is, well, if you ignore this fast factor, is this one.
I forget, does Keating come up with this by sort of moments, or do they, I mean, this is coming from maximum Brownian motion condition, but Maury, what's his name? Bramson?
Bramson?
He answered that many years ago.
So he answered it for the branching random walk.
Yeah, but for Keating and Yari and Fyodorov, how did they come with it?
I'm not sure, but there are analogs for random matrices too, so it could be that they looked at that. Right. So what I will try to explain now is to how you come up with something with a guess like that, and then I'll try to explain what happens when you look at the event. It's still 50. 50 minutes.
Yeah. Plus.
Okay, so what happens here? What is really at play? So I already told you that these things are Gaussian. So we have Selberg's central limit theorem. And in Selberg, it doesn't really matter if you twist by p to the x, you still get a Gaussian. So if you look at zeta 1/2 plus IT plus IH, and you look at the same thing for a neighboring value, let's say H prime, then usually you expect them to be of a similar order of magnitude when H minus H prime is less than 1 over log T. Right? So you can think of this by looking at the derivative of zeta, or you can think of this just by looking at this random model here, and say it's just because of Taylor, basically. The reason is because p to the IH prime in this case is p to the IH plus O of log P over P log T. And basically this thing is negligible on average. Sorry, there's no, it's just log P over log T. So this is negligible on average. On average. Okay, so when I look at the maximum, I shouldn't really be looking on the whole plane, but the first thing I should be doing is to do to just focus on points that are spaced 1 over log t, at least. And one first guess would be that, okay, well, they're perfectly correlated, basically perfectly correlated in this regime. So let's for simplicity assume what happens if they're perfectly uncorrelated away from this regime. So what if the values are perfectly uncorrelated or almost perfectly uncorrelated? When h minus h prime is bigger than 1 over log t. So if this were to happen, then I would have, then I can basically think of, this leads me to think of, for every point, then I have Zn, Z1 up to Zn, Gaussian random variables, of mean 0 and some variance sigma squared. And n here would, so it would be that n is log t and sigma squared is 1/2 log t for zeta. And it would be that n is log x and sigma squared is pi squared over 12 log x for tau. And I can think about what happens when I have completely dependent Gaussians and independent Gaussians of some variance. What happens to the maximum then? And this is just a calculation. So if independent, then I can take the probability that the maximum of the zi's is less than some u, is the same as all of them being less than u. So if I assume independence, it's just factors as 1 minus probability I bigger than u to the n. And if you do a little bit of asymptotic analysis in this quantity here, then you end up seeing that the threshold value is u star equal to so it's square root of 2 sigma squared log n 1 minus log n over 4 log n. The threshold is when this probability goes from being basically 0 to 1. A little bit below this, it's 0. It's 0, a little bit above this, it's 1. And so if I do this for zeta, it gives me this prediction, but instead of 3/4, 1/4. So this leads me to the prediction that for zeta, the maximum should be something like the maximum of zeta should be something like log t over log t to the 1/4. Almost sure. Which doesn't agree with the conjecture of Fyodorov here and Keating. Okay, so where is this 3/4 coming from? Well, it comes from correlations. So this assumption is too crude. The values are not perfectly uncorrelated. There is some correlation, but is actually insignificant even when h and minus h prime are quite far from each other. And one has to understand this kind of correlation and how it affects the distribution. So the problem is, it's wrong due to significant correlations. So the right way to model zeta, when you look at not just a fixed value, but this path of values between 0 and 1, is so if I look at log of zeta 1/2 plus it plus ih, so it should be so what ends up happening, you have to do some sort of, this is the right scale to divide things up. So maybe let me call this yjh. And what ends up happening is that you can basically think of this yjh prime to have some sort of dichotomy. So perfect correlation when h minus h prime is less than 1/2 to the j, and perfect discorrelation well, you have to take all of this with a grain of salt because they're not quite true. But this is just a heuristic. And then it become discorrelated when in this regime. So what ends up happening here is if I write h as m over the capital J, let's say, go there. What ends up happening is that you get this kind of branching structure. So let's say that the first thing tells you the top digit of m, maybe dyadic digit, maybe the top digit is 0 or 1, and then the second most important digit is 0 or 1 or 0 or 1, etc. So what happens is that if m and n, h prime, if m and n agree on many top digits, this means they will share a large common path, and then they will just become, the rest will become uncorrelated. Right, so what happens here is that for every, so this is the top digit, this is the second most important, second top digit, binary digit, etc. So what happens is, if you want to compute the correlation, let's say between this point and this point, you look at where they split. Well, these ones split right away, so they're perfectly decorrelated. But if you look at this and this point, they share a lot of digits, so the distance between them is close, which means that a lot of their summands are basically the same, and they become perfectly correlated. And yeah, so this is the right structure. And this is the right model, which is a branching random walk. Maximum of this kind of walks, and actually the branching Brownian motion was studied by Bramson. That was the first work that studied things like that. And what ends up happening is that the maximum is dominated by a small part of the tree. So when you, because of these correlations, if you do some sort of, if you just try and do some second moment method, the maxima here are, so the find maximum or typical maximum, we must focus on H's such that when you look at, let's say, what happens up to K steps. Okay, so these are independent things, and their variance should grow linearly in J or in K. And maybe the target is M, so this would be maybe M plus B. So what happens is, if you want to reach maximum M, all the way you have to sort of stay below this linear barrier. The reason is, if you go a little bit above it, you have somehow cheated your way at this point to make the maximum. But this is an unlikely event to cheat your way at this point. So you have to focus on this linear constraint, and this has the proportion of H's that satisfy this is something like 1/J. Maybe depending on this B also, B/J. But this B is typically pretty small, so it's really like 1/J. So you have to basically throw out most of your tree, because most of your tree is not really gonna give you the maximum. The maximum is gonna happen when things align very well. And this extra, because you have shrunk the N here, basically, that N, you have to go from 1/4 to 3/4. Okay, so what about this T function in the so for this
in their work, of course, it's quite tricky to make this model rigorous, and they need fourth moments and things like that, and they need mollifiers or mollifier. He was calling it a twisted something. In your case, is it much easier for the divisor? Or tau? What do you call it? Tau?
You mean to go down to this level?
Are you claiming the answer is the same? Maximum? Okay, maybe you state your theorem and then we'll discuss the proof.
Okay. It should be similar and easier to prove, but yeah, let me just explain what is going on for tau. So there is two differences for when you look at tau. The first difference is you're no longer Gaussian. So I said you're Gaussian, but I lied. You're only Gaussian in the regime of small deviations from the mean, of normal deviations from the mean. When you go to the regime of large deviations, you're no longer Gaussian, you're something else. So first complication, first difference for tau, you have non-Gaussian tails. In regime of large deviations. And actually, there is another complication. There is a dependence on how many product factors you have. So somehow you have to first condition on how many factors you have, number of divisors. And the third one is something I have been avoiding to do so far. When you Taylor expand this thing, because the 1/p to the 1/2, everything after the second term and onwards is not important. But when you Taylor expand the other thing, then you get pretty important correlations for different. Okay, so if I Taylor expand this product, then I get the sum over P of x, and then I get the sum over BP, and 1 of infinity minus 1 to the n minus 1 over m, p to the I mxc. If I haven't messed up. And so this is gonna give you correlations when xc prime over xc is close to a 5 fraction of small denominator, a small numerator. So you have to worry about a lot more things being correlated. But the good news is that when A and B is not a fraction 1, A over B is not a fraction 1, these correlations are a little bit small, a little bit too small, that you can basically treat the thing as if they were independent. But this requires a really very delicate analysis. So this means delicate analysis. Sort of discard pairs with A over B less different than 1, and only focus on the ones that are close to each other, just like for zeta. Okay, so let me tell you maybe just a theorem, and I'm going to stop here.
In your main problem, you put the maximum of xc between 1 and 2.
Yes. So the theorem is, like I said, this is work in progress, so we don't. Did I actually write down the theorem? That's a good. So we have the upper bound for now, and pretty confident about the lower bound too, but not we're not down to the 1/4, 3/4 analysis yet, because we have not inserted this kind of random walk conditions in the arguments. So it's okay, new row log x. So what are all these things? For almost all n less than x with rho times log x prime factors. And as I told you, you have to condition on the number of prime factors because the answer depends on that. And where this new row is the solution to this implicit equation. Okay, and now I need to tell you what this lambda star is. L star is something called the Legendre transform that appears naturally when you do large deviations for things that are non-Gaussian. So what is this L star? So L of S is log of the integral 1 plus e to the 2 pi theta to the s d theta. Then you define alpha u implicitly by this equation. This is the saddle point alpha u when you do your asymptotic analysis in the large deviation regime. And then we define L star of S to be S L prime of S minus L of S when S is alpha of U. It is what it is. This life one has to work with these things because you have non-Gaussian tails. And when rho is 1, to go back to the question of Holland Tenenbaum, so this rho is 1. So what is nu of 1? So I'll just write here nu of 1 just compute this, it is equal to, well, it's a transcendental thing, of course, but. And it's actually strictly less than log 2. Maybe that's maybe it's the most important property that is strictly less than log 2. Okay, so I'm gonna stop here. Thank you for your attention.
Actually, that's the true order of magnitude.
Yes, and I think we can prove this, but there is a lot of work to be done, and
Well, I think,
we should have some 3/4 kind of analog, which I didn't. I have it in my laptop, which I forgot to copy down here. But there should be a secondary term with certain constant 3/4 triple log of x. And again, there should be some conjecture like the one Fyodorov here keeping.
If you place it with your random model, do you have all those results ready?
No.
so the difficulty lies in the probability, not in the reduction.
Yeah.
So that's what I wanted to ask, two things. One is, in their reduction, it was still quite, they had to use modification. You're not doing.
We don't. It's easier to reduce.
It's an easier.
Yeah.
And
Because we don't have to.
And one thing that, in the way you presented it, that seems confusing to me, is you'll always have points C primed over C, which are got small denominators in C and C primed in 1 and 2. And those points are the bad points, if I understood the way you, or is other points, how do you get this bound? You're not averaging over C, you're taking maximum over C.
Yes.
So surely the worst case is coming from C and C prime where their ratio is an integer or half an integer, or is that? Where's this coming from in that analysis, the way you presented it?
You mean this kind of thing?
Exactly there, yeah.
Oh, you have, okay, I can show you that.
Because you're not averaging over C.
So if you just take this expression and you multiply it by the same thing for some C prime and compute the expectation. And take the same thing. When you compute this expectation, then you're gonna get like things like you're gonna have here a double sum mn and you have p to the I mxc minus mxc prime. So if you happen to choose m and n, so that this becomes basically 0, you're gonna get
diagonal.
perfect variance, perfect correlation. But you have this factor, which help the 1 over mn.
So all those terms with small denominators are part of just the diagonal variance main term.
Exactly. Yes, it's sort of a diagonal.
Okay.
Yeah. Yes.
So, do any of these questions become non-trivial or interesting in the permutation model?
Right. You could ask the same thing. You would put so that you would have to do sum over all invariant sets of n. You have to do, I guess, e to the I CA, such that sigma A is A. Yeah, and you can ask the same question, and I expect to get the same results.
But it's sort of equally difficult or something.
Yeah, you don't. I think so. Yes. Yes.
And the function field case is expected to be the same as well. Is that really different because of the discrete nature of the
I guess this is also discrete, so maybe I spoke too.
Definitely, I think if you start pointing terms out to 1 plus 2 or 1, then this might throw up differences in some of them anyway.
Oh,
In fact, the 2 and 3 and 4 are not times.
okay, so maybe it's not quite the same. Sorry, maybe I spoke too.
If you never thought about it before, you don't need to think about it live. So.
Yeah, it's discrete, so you don't get a good distribution, you get something that's periodic.
Any other questions? Okay, let's thank Dimitris again.